Okay, great. So let me get started. It's great to be here. And today I'm going to be talking about challenges in both building and evaluating natural language generation systems, specifically long-form text generation. So just a bit of background, although this is probably familiar to most of you. This talk will focus on language models. So language models are essentially trained to predict the next word given some prefix as input. So here, given cats like to, the model computes a representation of this prefix and uses it to predict the next word sleep. So it's a very, very simple training objective. But if you scale up this neural network over here to have hundreds of billions of parameters and train it on a huge amount of data, the models tend to exhibit some very impressive capabilities. So this is a figure from the Palm paper that came out of Google earlier this year. It's essentially on the x-axis showing you the model scale. So how many parameters are in this neural language model. And on the y-axis, you have kind of an average score over several different natural language processing tasks. So this dashed line here, represents the performance of an average human on these tasks. And this line up at the top represents the performance of a human expert. So you can see that as you scale up the size of these neural language models, the performance goes up and up and up. And of course, this is a very specific collection of tasks, but you can see that in general, their performance increases quite dramatically. And so this region right here is not really accessible to academic researchers or even most industry researchers, but it is a region where we see so-called emergent properties coming out of these language models. So things like ChatGPT and Palm, they're capable of things that many other language models are not. So all this to say that this very simple training objective of predicting the next word has kind of revolutionized the field of NLP. So my lab's research focuses specifically on the case where the inputs and the outputs of these language models are very long and complicated. So here you see on the input side, if you feed in, say, like a book or a chapter of a book, you will run into several limitations of the model. Their input size has a maximum word limit. So anything beyond that word limit is usually truncated, or there are some other hacky solutions to get around this. Another problem is when you predict the next word, this is a kind of very local training objective. So you can usually do this with only the last 5 or 10 words. It's very rare that you need thousands of words of context in order to predict just the next word. So we've found that these language models tend to ignore a lot of the distant context when they are processing an input. On the output side, kind of similar to what we saw in the previous talk, there are many issues with the outputs of these language models, and these only increase as you generate more and more words from the language models. So we observe things like hallucination, repetition of phrases or sentences. And broadly, there's no explicit planning component of what the language model is going to write. The language model is just going step by step. any planning that it's doing is implicit within the model's parameters. And it's clear that with things like ChatGPT, there is some sort of long-term planning happening, but we have no insight into what that is. And oftentimes it's very clear, especially as you generate more and more words, that this planning component is quite limited. So in this talk, I will focus on two projects that have been done by my lab. One is an application of these models and integrating them with retrieval to solve long-form question answering. The second project is methodological contribution on trying to address some of the issues with long-form text generation using language models. So this work I'll talk about first is called Hurdles to Progress in Long-Form Question Answering. The models here are not actually very important. What I do want to highlight is some challenges with collecting a data set and evaluating this task. So this task of long-form question answering involves getting a question like, why do humans need to eat many different kinds of foods, but cows only need to get grass to survive? And you want a model to generate some sort of multi-paragraph long answer to this question. So there's a data set that is crawled from Reddit that the community uses to work on this problem. So let's take a look at the common pipeline for long-form question answering. We get this question, and the very first thing we do is retrieve documents, like evidence documents that we can use to kind of gather evidence and information and use it to generate our answer. So I might retrieve an article on the cow's digestive system and the human digestive system. I will feed both of them into my language model along with the question and have it synthesize all the important information and generate an answer. Because this task involves both retrieval as well as generation, the evaluations for the task have a mixture of both. So we evaluate the retrieval model. How often does it retrieve articles that are relevant to the question or contain the answer? And also we evaluate the generation aspect. So this Rouge score might be familiar to some of you who have worked on summarization before. It's essentially measuring the string overlap between the generated answer and a reference answer, which might be some like Reddit-based answer. So I'll briefly go over the method that we and many other people use to kind of tackle this task. The first is, how do you train your retriever? So given this question, we want the model to retrieve a bunch of relevant articles. And so what we do is we take advantage of advances in dense retrieval, which means that you take this question, you map it to a single vector, and we don't have like gold data on, given a question, what are the best documents to retrieve? That data is not easily accessible. So we do the next best thing. We take our training data and we map we take all of the answers in the training data, so hundreds of thousands of answers, and consider each answer to be a document. So if you do this, you can now map the vector of the question to be as close to the vector of the correct answer as possible, and as far away from some randomly sampled incorrect answers as you can. So you have this kind of contrastive retriever that you can train. And you can use any embedding model for this. We use BERT here. So given this retriever, we can then, given the question, retrieve some articles. And now we have another challenge. I already mentioned that the language models have a limited context size. So how are we going to get the language model to condition its generation on these articles that we've retrieved? So there have been several advances in transformer-based language models, specifically around the self-attention mechanism, making these more efficient and scalable to bigger contexts. We use a variant of self-attention called routing attention. So in routing attention, instead of computing the full self-attention over the entire context, you first do a clustering over the entire context. So in this task, my context is the question and 8 retrieved articles, like the full text of those articles. All of them are concatenated together to give you a context of 8,000 words max. So doing attention over 8,000 words is infeasible. Instead, we'll do a clustering over these 8,000 words using like k-means, and we will do attention only within each cluster. So we're not going to ever compute full attention over 8,000 tokens. So using these kind of tricks, we can get this model to generate long-form answers conditioned on questions and retrieved articles. And at this time of this project, which was last year, we were able to get the state of the art on this explain like I'm 5 data set. So that's not the point of this this talk. State of the art is kind of meaningless for this task because the evaluation metrics are not well developed. So one thing that we wanted to know is, how is our model using the retrievals? Like, is it actually quoting text from the retrieved passages? How is this text useful in any way? So we did an experiment where at test time, we replaced the retrieved articles with completely random articles. So for that question about how is the cow and human digestive system different, I might replace these retrievals at test time from cow and human digestive system to something like how does a car engine work, or some completely unrelated topic. And we observed that the performance of our model, the quality of the answers barely changes at all. So this indicates that the model is not using the retrieved articles at all. And this task is very difficult to evaluate both the retrieval and the generation at the same time, because there is a connection between the two. And that is what we're missing with all of these kinds of evaluations. So we found that with a human evaluation, humans in fact prefer answers that are generated conditioned on random retrievals than on the actual relevant retrievals. So there's something majorly going wrong with our setup here. Retrieval is not necessary at all. So it turns out that there are several issues with this task setup and the evaluations that people have proposed in the past. The first is related to the data set. So we did an analysis of why retrieval is not useful, and we found that actually many questions that are in the test set of this data set are paraphrased, and they are included in the training set as paraphrases. So for example, here, can you protect electronics from solar flares or EMPs? This is a validation set question. We have 6 or so training set questions that are very, very similar semantically to this question. So you can see how the model doesn't need to retrieve to answer these questions. It's already seen the exact question in paraphrased form in a training set, so it could just spit out one of these memorized answers, and it is completely agnostic to the retrieval. So 80% of held out questions are, paraphrased in the training set. Another problem is that Rouge, this string overlap-based evaluation metric, is not meaningful for this task. So for this question about EMPs, we can retrieve a completely random answer to this question. So here's one about the fast lane and slow lane. It's about like roads. It has nothing to do with solar flares. It gets a Rouge score of 19.4 versus this is a gold answer written by a human. It receives a Rouge score of 18. So you can see that this metric itself is very limited. Finally, you might imagine, all right, what if we just do human evaluation? So we recruit some humans to read these answers and say which one is better than the other. The problem is, if you imagine for this question, you need to have a background in the subject. You need to actually understand how EMPs work. Otherwise, it's not possible for you to answer this question, right? It's not possible for you to evaluate the correctness of any answer that is generated to this question. So there are many different issues that present themselves when we're working on long form text problems. These are some of the examples with this question answering task. And these are present no matter how big the models get, or no matter what kind of data they're trained on. This is kind of where the field should be heading, is developing better evaluation protocols, higher quality data sets. As the capabilities of these models continue to improve, we need ways in order to properly measure what kind of abilities they're capable of and have a way to make meaningful progress on text generation tasks. So yeah, this is another slide showing that Rouge is just not a meaningful metric. A random training answer gives you a Rouge score of 16 on the validation set. The best human written answer, like the most upvoted answer on Reddit, only gets you 26. So you can see that there's a very small range in which you can make progress here. So I just wanted to end this part by showing a generated answer from our system. So this is a question: why are almost all boats white? And the system starts out well. It generates boats are generally painted white. They're inexpensive, easy to clean. I guess that's debatable. Ships are also painted to provide visible visual contrast. But then it kind of goes off the rails. It starts talking about it's easier to spot, which is a good thing if you're a pirate. It's clearly not a good thing if you're a pirate, and also pirates are not you know, a reader of this answer in any case. The highlighted text here is showing repetition. So the model is just generating some text that it already produced before. You can also see it produces some Reddit type language like edit : blah, blah, blah. The model, of course, is not editing this text. It's just generating it. So these problems are present with all sorts of language models to different degrees. And that kind of brings me to the next part of this talk, where we can look at a way to actually fix this kind of problem or mitigate the issue. So this work is called RankGen, and it was just presented last week at the EMNLP conference. To motivate this, I wanted to look at larger scale language models than in the previous part of the talk. So previously we had discussed a fairly small scale language model that was trained from scratch. Here we'll look at GPT-2, GPT-3, and Bloom, some fairly large scale models. So if you were around when GPT-2 was released and you were paying attention to the field, you're probably familiar with this particular example. In a shocking finding, scientists discovered a herd of unicorns living in a previously unexplored valley in the Andes Mountains. So this was a prompt that was fed to GPT-2, and it actually generated some coherent follow-up continuing this prompt. And everyone was impressed because there had been no model like this up till that point that could produce coherent, imaginative text like this. So I want to look in more into how this process actually occurs of generating this text, because I've kind of glossed over that to this point. But first, let's look at what these larger scale models of today produce. So first, we have the opportunity of the easiest possible way to decode from these models, which is greedy decoding. So in any language model, you're given this conditional distribution of the next word given all of the words that you've seen before, right? So this is a probability distribution over your vocabulary of your model. And to generate a word in greedy decoding, you will just choose the word that has the highest conditional probability and produce that. So it's very straightforward. If you take Bloom, which is 170-ish billion parameters, or GPT-3, and you generate text from this unicorn prompt given using greedy decoding, you see repetition, this highlighted text. You can't read this, but just believe me, it's repeating itself. And the text that's not repeated is actually very dull. So it's kind of generic text that's not very specific to this context. So greedy decoding is not really used by most people when they are generating text from their models. On Another option, which is also straightforward, is ancestral sampling. So here, instead of just taking the argmax of this conditional distribution, you can just sample from the full distribution. So if you do this, you avoid problems with repetition, which are very, very present when you're using greedy decoding or beam search. But you very quickly veer off topic. So the highlighted text here on this side starts talking about like taxation and US tax laws and social security numbers and has nothing to do with unicorns discovered in the mountains, right? It's interesting. It's probably more interesting than before, but it's also not something you would like to generate. Meanwhile, GPT-3 here is talking about loggers cutting down trees, and so it's still unrelated. So what is the most popular decoding algorithm today is a form of truncated sampling. So instead of taking the most probable word or sampling from the full distribution, we do truncated sampling. So we chop the distribution off at some point. The most popular method is nucleus sampling, where you take the words that cover 98% of the probability mass and you discard the rest, and you only sample from those high probable words. But here I've still highlighted that there are numerous issues with even this sampling algorithm. So you get repetition, even with models like GPT-3, there is no perfect decoding algorithm. That's why when you are actually using this model, you tend to generate multiple completions for every prefix and pick the one that looks the best. So that unicorn example from the GPT-2 paper was a result of 10 or more tries, where the other 9 tries were garbage. They were repetition, there was hallucination, going off topic, and so on. So why does this happen? I mean, this is a critical question, right? We've trained these huge scale language models. They are doing a good job fitting their data. Why is it that when we go off and generate long pieces of text that they have all of these issues? So there's kind of 3 broad categories of issues with the models. One is, kind of uninteresting. So maybe the language models are still not big enough, and maybe we're still not training on enough data. This is something that, is not relevant to anyone but OpenAI or Google, right? No one else can make progress on this front. Another more interesting reason is that we're using the wrong training objective. So maybe predicting the next word, although it has quite impressive capabilities when scaled up, is still not the best way to generate text. And maybe we need some other objectives that can be less prone to these kinds of problems. And the third thing is we have a wrong decoding strategy. So we still haven't found the best way to generate text from a trained language model. So our work falls kind of in the middle of these two and does not touch on just blind scaling the language models. You can probably tell how I feel about that. Let's get into this method, which we call rank gen. So this method is basically the result of an experiment that we did trying to analyze how language models understand long pieces of text, not just predicting the next word. So this is a snippet of the book Peter Pan. And we did this experiment where we selected a random sequence of sentences from this book, which we call the prefix. So this is what is fed into the language model as input. And now we know that the next couple sentences are what we call the gold suffix. These sentences immediately follow the prefix we selected. We also, in our experiment, have a random suffix. So this is a sequence of sentences of the same length as that gold suffix, but it occurs elsewhere in the book. It does not immediately follow the prefix. So any human would be able to tell you that the gold suffix is the one that follows this prefix and not this random suffix, right? The random suffix is completely incoherent when you're given the prefix. However, even the biggest language models struggle with this experiment. So the question is, given the prefix, does a language model prefer the gold suffix over the random suffix? In other words, is the probability of the gold suffix given the prefix greater than the probability of the random suffix given the prefix? So this is just a binary test. What probability does a language model assign to each case? And random guessing will give you 50%. You can see that even GPT-3 struggles here. It only gets 78% of these examples correct. Humans are at about 94%. So there's a big gap when you're trying to use these language models to assess the probability of longer pieces of text, not just the next word. Clearly, they don't do a good job of modeling this probability. So why is it that these random suffixes are so often preferred? Sometimes they might have high likelihood words in isolation, so like frequent words or entities that also occur in the prefix. And also we know that language models tend to ignore the long-term context to focus on local context. So maybe it's ignoring the prefix when you're kind of deep into the second half or whatever of the random suffix. So our model is based on correcting this problem that we discovered. So in RankGen, we encode all of these prefixes into single vectors using a T5 encoder. We similarly encode all suffixes into a single vector. So now we train this model to, again, similar to the contrastive loss I described in the question answering project, map this vector as close to the gold suffix vector as possible and far away, that's these dashed lines, from all of the other suffixes in the batch. So this is a case of in-batch contrastive learning. This only works if you have a very, very big batch size so you can get as many negatives as possible. So I won't go into the weeds too much, but in essence, we have a positive pair, which is the prefix and the gold suffix, and the negative pair, which is all of the other suffixes that are in the same batch as this suffix. Another type of negative that we include in RankGen is a a model-generated negative. So we take the prefix, we feed it to GPT-3, generates some text. We know it likely has hallucinations and other artifacts, so we treat this as a negative and we force RankGen to disprefer these model generations over the gold next continuation. So you can train this at scale with large in-batch contrastive learning. And this is kind of equivalent in the going back to the training objective case of something like K-word language modeling, and just instead of just next word prediction, now we're predicting the next sequence. So, okay, we've trained this model. How do we actually do generation using this RankGen model? Because it's not a language model. It's unclear how you can generate text from it. We basically integrate it with an existing model like GPT-3 or any other big causal language model. So the first strategy is very straightforward. You take your language model, you generate, say, 20 different continuations of the prefix from the language model, and then you encode each of those continuations using RankGen. So you get a vector for all 20 of these generations. You similarly encode the prefix using RankGen, and then you can just measure the dot product between this prefix and each of these suffixes. And the one that has the highest dot product is the one that you choose eventually. So this is a very easy strategy for kind of improving the generations from your language model. You just over-generate and re-rank using this model. That's why it's called RankGen. So for sake of time, I won't get into how you actually integrate this model into beam search, but it is very straightforward. Essentially, you're just doing this ranking step at multiple time steps in the generation process rather than all at the end. So I'll skip over this part, but this beam search with RankGen seems to result in even higher quality text. Okay, so how do we evaluate? This is another extremely complicated topic. How do you evaluate open-ended text generation? We use this metric called MAUV, which was presented last year at NeurIPS and won an outstanding paper award. Essentially, it's measuring the distribution between the difference between the distribution of human written continuations and model generated continuations. Of course, that's glossing over how it actually works, which is not in the scope of this talk. So MOV will give you a score from 0 to 100. And we can see all the decoding algorithms that we have talked about in this talk so far. Greedy decoding is really bad. It has a lot of repetition. Its MOV score is only 15. Ancestral sampling gets a much higher MOV score of 74. The truncated sampling approaches are slightly better. And RankGen with beam search is significantly better than all of these options. So this indicates that using RankGen along with an existing language model is a great way to reduce some of these artifacts that are occurring with standard language models. I just wanted to show that on the right-hand side here, you see the cost of RankGen. Okay. All right, great. Sorry about that. So this is the cost that you pay, is that the decoding is much slower than with normal sampling algorithms. And this is something that we're actively working on to reduce. So I just wanted to conclude by showing some comments written by human evaluators of RankGen decoded text. So we see that human evaluators prefer RankGen text over nucleus sampling generated text 75% of the time. And they say reasons for their preference include that the generation is more relevant to the prefix. It has better continuity, better coherence, stylistically more similar to the prefix. Broadly, it's just a better fit for the input to the language model than otherwise. So I'll conclude with a plug to use RankGen. It's very straightforward. You can pip install it. You can run it in just a few lines of code, and you can use it with any pre-trained language model that is on Hugging Face to just kind of automatically improve the quality of the text that you're getting from these models. So with that, thank you, and happy to take any questions if there's time.
Hello. Yeah, thank you for the great talk. I just had one question. In one of your slides, you mentioned that conditioning the generated texts on random samples was not better or not worse than generating it on the actual true samples or the gold standard samples. So why that observation? Or what is the reason?
So this was specifically regarding the retrieval component. So text that was generated conditioned on random retrievals was even preferred over text generated on the model retrievals. Some of the reasons for this are the model is not actually sensitive to the retrievals because of the train validation test leakage issue that I mentioned. This leakage is actually quite difficult to stop because it's paraphrase based. So if there's a paraphrase of your question in the training set, the model no longer needs to do anything in order to generate the answer. It just needs to memorize the training answer and spit it back. So the preference that we saw was, probably not significant to random retrievals over model retrievals, but it essentially showed that there was no preference to model retrievals, which is more important. The retrieval component was not being used.
Yeah, I had a question. So I think Mohit, you had started your work with quanta type of data sets, right? It's like quiz bowl, reading comprehension type of data sets. So I was wondering, like, what is the state of that in terms of this models? Have you tried those models on quanta or quiz bowl competition data sets? Yeah.
Yeah, so the question was about some of the work I did during my PhD on trivia question answering, which is, similar in some ways to what I presented here, but slightly less complicated. So I think my PhD advisor has been continuing this line of work. The models are much better than humans at this current state, and models like ChatGPT, I think, are probably significantly better, although they haven't been tried yet. So now there are many other challenges on, for example, how can you write a question that fools one of these huge language models? That's a more interesting direction that that work is progressing in.
Yeah, thank you for the great talk. So when you are showing this random suffix and gold suffix, have you chosen the random suffix carefully, or it is just randomly chosen?
That's a great question. So we did both, actually. Maybe I can go back to this.
And is there a difference in result when you choose?
Yeah, so I didn't mention this in the talk, but there are two settings we tried. One is with the random suffixes chosen completely at random. The other is called a hard case, where we use a trained model to select like the hardest random suffix that we could find. And then we ask, so we observe that human performance also goes down when you have these challenging random suffixes, but model performance degrades even more. So we see that it's only slightly better than random chance when you carefully select the random suffix. So when you have a more challenging case, it requires much deeper reading of the prefix and the suffix to figure out exactly why they're not incompatible. That's why I think a human can always figure it out, but we have humans who are, they're trying to do the task as quickly as possible, so they may not be reading too deeply.
Sure. So coming to this, when you proposed your previous model for routing transformer,
Right.
so you were doing clustering. So aren't you missing this long range correlations or long range dependence?
Yeah, so in that previous work, the clustering is essentially a trick to make the model be able to handle very long inputs, but you do lose a lot of the long-term dependencies that it can happen that you have a cluster where several of the words are, thousands of words apart, but this rarely happens. In practice, the tokens kind of cluster together in proximity to each other. There have been many other approaches proposed to handle long distance dependencies and transformers, but none of them actually work reliably. That's why you see the big labs like Google and OpenAI, they are just training dense transformers with as much context as they can fit, because these sparse kinds of alternatives end up hurting performance at scale, and you don't get any reliable benefits of extending the context with this particular next word prediction objective. I think probably what we really need is newer training objectives that are designed to, kind of encourage the model to capture better representations of a long range context.
Yeah, sorry, I have a last comment.
Sure.
So do you feel, are we training too foolishly the entire thing?
That's a great question. So it's do you feel like we're training too foolishly? And by we, I assume you're referring to the big tech companies. I have mixed feelings towards this approach. First, I should say that you can't deny the results. There are no models that previously have ever come close to the capabilities of something like Palm or ChatGPT. And clearly the curves show that we have not exhausted the gains that will emerge with arbitrary scaling of these models further. However, I do think that the industry labs are solely focused on this direction at the moment. They are not really considering scaling other variants or other model architectures other than the transformer. No other training objectives have been considered. Probably the most compelling advance outside of next word prediction has been the instruct training that OpenAI has been doing using human labels to kind of guide the models to improve them further. But unfortunately, we have no numbers to back up how much of an improvement that has actually contributed, or if it has been integral to anything at all. So kind of the closed off nature of these companies makes it difficult to assess. But I think academia has a lot to offer in terms of doing more experimentation with the training objectives, the modeling architectures. But it's a kind of sad state of affairs, because to prove that it actually works, you need one of the companies to pick it up and scale it, because it's currently, we don't have the resources to compete. So thank you.
Yeah, so thanks, Mohit. Here is a small token of appreciation for your great talk.